Lucky you, I managed to join my lecture online. Like I said, do it all the time.
It makes sense that you can.
No, I can't. I only have 3 uses of the online lecture option for this entire semester. I just used my second one. I only have 1 left. That's done. What are we gonna do right now? Send me a schedule.
the audio. And okay, I hope you guys who are online can hear me. I'm going to open this channel or chat just to confirm it before I move forward. Okay, I'm going to get back to the chat. Oh, okay, we will start. Yep. I'm still trying to check. Chat. Okay, it's the top item. Okay, so someone just confirmed that they can hear me, so we can now get started. All right, so as I said, I'm going to give you a question. It's part of the final exam of 2022 spring. So that's about a year ago. All right, so this is a question. So we have Tristana, Ishan, Jane, and Lashes, and also Athleen. They're friends in the same class of 26 students. When they arrive at school and line up in a class-specific single file to get ready to enter the classroom, they prefer to be together. So there are how many people? 1, 2, 3, 4, 5 people. So there are 5 people who prefer to be. You may assume that the order of arrival of students is random with no specific distribution. But normally, when people arrive, there's a certain distribution. It's called the Poisson distribution. If you understand the statistics part of it, but we assume that it's all random. Okay, it's completely random. What are the chances that these friends are contiguous? In other words, they are together. Okay, as a group of 5 people in the class-specific single file, you may assume full attendance. In other words, do not assume anyone is absent. The class has 26 students and they're all arriving just at random order. To think about this question in an easier way, you can think of just students A, B, C, and D. And think about all the ways to end up with A and B being together. In other words, you scale the problem down to the point where you can enumerate all the possible cases. And by looking at the pattern, when the size of the problem is smaller, hopefully you will find a pattern to help you find the solution to the larger problem. So in this case, if we only have 4 students, A, B, C, and D, then we have A, B, C, D as one way to arrange the 4 people, with A and B being together, B, A, C, D, B, B, C, A, and so on. While A, B, B, C, I'm reading this part here, while A, B, B, C, and B, C, D, A do not, because in those cases, A and B are not together. So this may help you formulate your approach. So this is the question. I can post it in an announcement so that you guys can have access to this question. So this is related to what we just talked about. It's related to permutations. It's related to probability, because we have to look at all the possible ways for 26 students to arrive. And then out of those possible ways, how many of those will end up with, in this case, these 5 particular friends being together. So are we good so far in terms of understanding the question? And once again, I'm not expecting you guys to get it done today, during class. Okay, so do this over the weekend. Yep.
This is memory person, right? Or something.
Not yet. I will do so. So this is one, and there's another one. So out of the 4 questions, the other question that I think we should be able to solve, especially after today's lecture, is this one here. A grower has 60 spots to grow a crop at the beginning of a growing season, and we are in spring. This is a growing season. The per seed germination rate is known to be 0.82, which means out of 100 attempts to germinate, 82 will succeed. This means that the seed has a chance of 0.82 or 82% to become a seedling. The grower guesstimates that a buffer of 10 seeds should be enough. This means that there are 70 seeds being germinated. We don't know how many will succeed. Hoping that at least 60 seedlings will be available for the growing season. Do we understand the question at this point? So we have 60 pots, okay, for the seedlings. So in order to make sure that we can use up all 60 pots, we are germinating 70 seeds, okay, with a buffer of 10. You are hired as a consultant to help the grower optimize the number of seeds to germinate. Compute the probability that the grower will indeed have at least 60 seedlings in this case. So this one is about the binomial distribution, which we'll continue to talk about today, because we're getting to the very last part of the binomial distribution. The really funny thing is one of my students, one of my best students from the previous semester, copied and pasted this text into ChatGPT, and back then it was 3.5. And ChatGPT was able to solve the problem step by step, providing full explanation and get to the actual conclusion correctly, 100%. In other words, if ChatGPT was to take this class, it would probably get a really good grade out of this class. You guys do not seem impressed or depressed. Because that's my expectation is that initially you guys would be very impressed. It's like, wow, I did not know computers can be so smart now. And then you get depressed because, hey, if the computer is just as smart as I am, how do I get a job? Are we good so far? Just to add to what I said, I think somebody used the ChatGPT 4.0 this time to take the final exam of a quantum computing class. And I can tell you it is not easy stuff, okay? Because I logged my own process of going through quantum computing, and I could barely dig through just the representation, the math part, okay? But ChatGPT 4.0 took the exam, the final exam, got a B out of the exams, and then immediately ChatGPT 4.0 was formulating an argument to argue for an A. It's like, no, I do not deserve a B, I deserve an A. So that was really kind of interesting too. Yes.
I feel like ChatGPT 4.0 has done so many impressive things at this point that we're all just kind of permanently depressed about it. It's like boiled over at this point.
It is still a mimic. Okay, in other words, it is still using text that we have written, as humans, we have written, and it's extracting, using abstraction, it's extracting information from the text. So I think, this is just what I think, because I really don't know enough about the engine, but I think we are still better in terms of the creative process. I think there's an internal thought process that you cannot describe in words, which is opposite to the way that ChatGPT works, because everything that ChatGPT does is based on words. It's based on predicting, what type of sentence, what types of words, what type of paragraph should be next. So I think there are still fundamental differences between us and ChatGPT, and it would be probably helpful for all of us, myself included, to find out, what the difference is, just so that, we still can find values that, only people can do, and, the AI cannot quite do that. And for those of you who want to kind of listen to more stories about this, one fully recommend, it has to do with the combination of ChatGPT and Furbies. Okay. And I do have one question in the previous exam about Furbies, but I'm not ready to quite let it go yet. So we'll talk about the Furby question, maybe next week or so. All right. So I will post the questions into the announcements just so that everybody has access to the text of the questions. All right, so moving on, this is about the big operators. I keep bringing this up because this is kind of important, both from the perspective of the operators themselves and also the understanding of the recursive definitions. And then we are back to the last part of binomial distribution. Last time we used proof by induction to show that the binomial theorem is indeed correct. This is a real theorem. So let's just kind of use the theorem and find out what it means. So the theorem says, as long as n is a natural number, p plus q, it doesn't matter what p is, doesn't matter what q is, okay? P and q are just representing two variables. So p plus q to the power of n can be expanded as a sigma notation, where we have I as an index variable going from 0 to n, and then each term that we're adding in this particular sigma is n choose I, which is the number of combination of choosing I from n items, times p to the power of I, times q to the power of n minus I. So you can double check and really quickly just say, what if n equals to 2? You get your typical binomial equation or expression. So to claim that this is true for every n is a big claim. So the way we proved this was to prove by induction, which is a very useful technique to prove theorems in computer science, because everything that we do recursively lend itself to proof by induction. But every single loop that you write, every time you use a while, every time you use a for in a C++ program, those can convert into a recursive representation as well. I'm not saying that the recursion as implemented in C or C++ is efficient, or you should use that to replace loops, but from the mathematical perspective, they have the same expressive power. Everything that you can do in the loop, you can do it recursively, and vice versa. Everything that can be expressed recursively can also be expressed using loops or iterations. But from the perspective of proving something, proof by induction works exceptionally well when something is defined recursively. I will have 2 examples to show you today in class of how to prove by induction. All right, so that's what we did last week, was to prove by induction. And then at the very end, we end up with basically the same thing that we were trying to prove, which is this thing here. So now the question is, okay, so what does that have to do with flipping a coin or probabilities? So in terms of flipping a coin, P can be representing the chances of landing on the head, Q can be representing the chances of landing on the tail. Okay, big deal. So in that case, what about the index I here? What is I representing? N is representing the number of coin tosses in a particular experiment. Okay, so you can say, oh, I'm going to flip a coin 50 times. But what is of interest to you? You can say, well, I want to see the chances of 25 times landing on the head and 25 times landing on the tail. In that case, I would be 25. You will be looking at just this portion of n choose I, p to the power of I, q to the power of n minus I, where n is 50 and I is 25. Is that okay? You go like, well, what does that have to do with computer science? I mean, this has a lot to do with gambling, and also, checking whether a coin is loaded or not, right? But what does it have anything to do with computer science? Well, you can look at it this way. You can say, let's look at P as the probability that a single bit gets transmitted using Wi-Fi or 4G or whatever. Okay, using some kind of transmission where there's noise present. So Q is going to be representing the same bit, being transmitted incorrectly or being received incorrectly. Is that okay? So P is receiving a bit correctly, Q is receiving a bit incorrectly. In that case, what do you think? Why do you think there's an interest to understand, generally speaking, what are the chances that I can end up with 4 bits that are transmitted incorrectly, 5 bits that are transmitted incorrectly, and so on? Why would there be any interest? Pick me. Okay. It's because you don't want your League of Legends game to be laggy and your champion gets killed before you even get to see what's happening. They're like, what? What does this have anything to do with League of Legends, right? Or any type of video game that has any real-time element to it. So has anyone ever tried to use your Wi-Fi connection at home, and the Wi-Fi router there's a microwave oven between you and the Wi-Fi router, and somebody decided, I'm just going to heat up my coffee, and then you lost your game. No one has that experience? Okay, some people have that experience, especially when your router is only using the older 2.4 gigahertz technology. The 5 gigahertz technology does not have this problem. So what is so special about the 2.4 something, gigahertz technology?
The same as a microwave.
It is almost, it's within the same band as the microwave oven, the frequency that the microwave oven, uses to heat up water and grease, okay? So the microwave oven has safeguards, okay? It does limit how much microwave energy is leaking out, but the safety standard is just to make sure that, someone who's walking by the microwave oven does not accidentally get cooked, or the innards do not get accidentally cooked. And it takes a lot of energy to cook a large organ like ours, okay? So that means there can be some leakage, and it's not a problem from a safety perspective, but from the interference perspective, it is still a lot of energy, because the Wi-Fi router is a very low power device compared to your microwave oven. So the probability is now coming in handy because there are ways to encode binary bit pattern where it is quote unquote, it has a self-correction capability. So you can have up to a number of bits being transmitted incorrectly, and there's enough information in the packet to self-repair, but only up to that many bits. Is that okay? Now, you can always change the number of quote unquote spare bits so they can repair more and more bits, but then you make the packet longer and longer, which also lengthens the transmission time. So there's a balance, where, okay, this is good because it will save me from retransmitting in most cases, and yet at the same time, it does not make the packet length too long, so that each packet takes too long to transmit. That is why the binomial distribution can be useful in computer science. So I want to kind of connect what we are learning to potential applications that you guys are not bored and go like, I'm learning this. This is just a checkbox. Every single class is a checkbox so I can graduate and move on to a 4-year university. Because that's not gonna help. Okay, if you look at classes as a checkbox, you may not be learning what you need to learn in order to get a job and stay competitive when you get a job. All right, so there is that. So now the question is, you have to connect this with the question that we saw earlier. So you have to connect this with not this one, but this one. Oh, so I correct myself. So this question is about the binomial distribution. Because how do we know? What is considered an experiment and what is considered a trial in this case? So whenever you see a problem that you need to solve in an exam or homework assignment, the first thing you need to know is to make a connection between the question and the definitions that we have already introduced in class. That connection is crucial as the very first step. So in this case, you have to identify. So in this particular question, what is an experiment? The experiment is trying to germinate 70 seeds. And each seed is representing a trial. So if we have a trial, what are the outcomes of a trial? We look at the seed, right? We put it on a little bit of a cotton. When I was a kid, I used to germinate beans, from a dampened or moist cotton, and then you put some water on it. So what are the outcomes? Either it germinates and becomes a seedling, or it does not. Those are the two possible outcomes. Okay, there are only two possible outcomes, which means maybe the bi part of binomial distribution is applicable here. So then you look further and say, okay, if the first seed germinates, does that mean the second seed cannot germinate? Am I removing a possible outcome because the first trial already has it? The answer is no. Okay, it is independent. Every single seed can succeed or fail. So that confirms that this is indeed a binomial distribution. And we have the probability too. The probability of 0.82 right here is going to be either P or Q, that we saw earlier. And then 1 minus 0.82 is going to be the other one. Now, which one you want to be Q, which one you want to be P, doesn't really matter, okay? Because in the end, you just have to make sure that the powers are correct. Does that make sense? And what are we trying to calculate as the probability? The probability says I need at least 60 successful germination. Okay, so that means if you have 61 successful germination, it's good. I mean, we just have one spare seedling, not a problem. 62 is fine, 63 is fine, and so on. So we just need 60, 61, all the way up to 70 as success. Okay, that would be the number of successful germinations. So I think that should help you formulate using what we just talked about. Okay, let me switch back to okay, it's not switch back to not this one here. Okay, so you have to find out, what is the range of the index variable that you need in order to get to the probability that we are trying to figure out in that question. So the rest, I will leave it up to you guys to think about, okay? Because we have a long weekend. This is Wednesday, and we're meeting again on Monday. So use that time to kind of try to figure out this problem. Are we good so far? I just want to give you guys an application, so that you guys actually have something to work on, and then we can talk about the solution. All right. So that basically marks the end of the binomial distribution thing, which is basically the end of the entire module over here. And the next thing we're going to do is to look into something that is kind of new to us. Not new to you, hopefully, but in terms of looking into the intricate details, it's going to be new to us. So we are going to look into the big O notation. How many people have heard about the big O notation? So most of you have. So can someone tell me, why is that significant? Why should I not look at it just as a checkbox in my education? Yes.
With the time and space complexity of an algorithm.
Okay, so the time and space. Would you want to add on top? Oh, okay. Okay, so it's about the scaling. Okay, so it's about scaling. In other words, if the problem size is n, what am I expecting as the amount of time it takes to solve the problem?
9 years.
But what if I double the size of the problem? So I did not tell you about the actual distribution or the actual function. So it is about the relationship between how much time it takes to solve the problem with respect to the size of the problem. If I double the size of the problem, does it double the time to solve the problem? Does it quadruple the time to solve the problem? Or does it just add one, to the, length of time to solve the problem? 1 unit, okay, of something. So that's why we are interested in the big O notation. So let's just say that you are becoming a software engineer and you need a sorting approach, okay? There's something that is given to you and you need to sort it. What are you gonna do? Okay, I think I'll give you 2 choices initially, and then we'll follow each branch, okay? So the 2 choices is, I'm gonna dig up, Professor who taught sorting algorithms. I think that's in CISP440. Subsidiary, okay, so that would be 430. Yeah, so I'm gonna dig up his notes and I'm gonna rewrite the entire sorting algorithm. I'm not gonna do that. Why? Because I'm lazy. Well, okay, to be more exact, if I did that, I would not be very productive, and then the chances of me getting fired or getting let go is higher. So I want to optimize my time so I can actually produce more useful code from the perspective of my employer. So what am I going to do? I can go to Wikipedia, right? To find the first sorting algorithm, copy and paste the C code of it, and call it a day. Well, guess which sorting algorithms are the most discussed from the undergraduate's perspective?
Bubble sort.
Bubble sort, insertion sort, and selection sort. Why? Because they are easier to understand. Okay. Particularly, I can't even remember the name, which one is which one. There's one where you look at you try to find the smallest element, you exchange it with whatever is taking the spot of the smallest element, and then you look at the rest of the array, and then you apply the same thing. Is that selection? Yeah, that's selection sort. So selection sort is very easy to understand, and it makes sense, right? But the time complexity is not really that good. It's only n squared, but it's not favorable when there are better algorithms to sort. So that means, selecting the wrong algorithm can be costly, both in terms of execution time and your job. I got to tell you this one story, okay? I know I'm full of stories, but this one is relevant as well. When I was writing my dissertation, I was using Word 2.0. Yeah, I'm that old. So I was using Word 2.0 on one of the first ThinkPads. This is a ThinkPad, but I was using one of the very first ThinkPad, which had a 10 megabyte hard drive. Can you imagine that? That's the entire capacity of the hard drive. So anyway, my dissertation has a lot of cross-referencing. Okay, so I would say refer to section blah 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 for a discussion of this. Okay, or going forward and saying, oh, this will be discussed in section blah blah blah. And the program got slower and slower and slower, but not in a linear fashion as I continued to write the dissertation. At one point, basically it just would not come back. I say save the file, and I can wait for an hour. It doesn't terminate. It does not. It doesn't get the job done. And I think in that case, it really has to do with time complexity. Somebody chose an algorithm that is inappropriate for what needs to be done. In other words, it turned the product basically unusable, at least from the perspective of writing a dissertation, which is not even long. My dissertation was less than 100 pages long. So we are not talking about a major publication or article here. It's 100 pages using 12-point font and double spaced. So it's not really that long, not a whole lot of content. And yet, the program, Word 2.0 could not handle it. So that means choosing the right algorithm based on the time complexity and also space complexity in many cases is really crucial, because if you choose the wrong one, you can end up having an algorithm your product does not work in real life. It might work in test cases, but it's not going to work in real life. So that is the importance of why we're going to talk about the big O notation, which is not exactly the right notation to use when you compare the time complexity of algorithms, as we'll see later in the next two lectures or so. So we'll go ahead and get started with a very simple algorithm, and then we'll just say, what is the time complexity of this algorithm? So this is an algorithm written in C, and its only job is to find the sum of the array of A. So array A is given to you with some values, and your job is simply to add up all the values within the array, the sum of all elements of array A. Okay, so I don't have to explain the algorithm too much. It's a very simple algorithm. I don't even bother to use a for loop. It's just a while loop with certain things initialized. So with this one, we want to look at the time complexity. So when you analyze the time complexity, you want to look at every single line and you ask, how many times am I doing this? And when I do this, how much time does it take? So this is only done once, right? Okay. The initialization of sum is also only done once. Now the question is, what about these two lines? What about line 8 and line 9? How many times are those two statements performed? N times, right? Okay, so it's exactly N. What about the comparison of I is less than N? How many times is that executed? N plus 1, very good. Okay, so that's the plus 1. Why is there a plus 1?
Because on the last comparison, it's not going to execute and terminate the
terminating one, the one time it becomes false is the last one, right? Because there are N times where N is less than N is true, and we continue with the body of the loop. But the very last one, which is the N plus 1 time, it is going to be false, then we exit the loop. So technically speaking, we execute line 6 N plus 1 times. So when we factor all of that stuff, then we can come up with a equation kind of like this one, where T1 is, okay, I'm gonna have to go back and look at my notation here. So T1 refers to. Okay, T1 refers to the amount of time taken by line 4 and line 5. T2 is the amount of time taken by the comparison, which is on line 6. And then T3 is the amount of time taken by line 8 and line 9. So this is the exact time. Okay, if you know T1, T2, T3, and T4, and also the size of the array, this will give you the exact time, okay, exact amount of time that it will take in order for that algorithm to execute. Which is great, right? You know, it's the exact amount. But sometimes you have algorithms that are more complex, such as the sorting algorithm and so on. So it becomes not as likely that you can figure out the exact amount of time. In other words, there might be terms in here. Okay, look at this term here. We have T1 plus N times T2 plus N squared times T3. So in this case, when N is large, the T1 probably becomes insignificant. Even the T2 becomes insignificant because N squared is going to grow a lot faster than N itself. So when N is large, the coefficient T2 is not going to be very important. Are we doing okay so far with all this? Okay. So now the question is, when we compare algorithms, you know, how do we do it? In other words, are we really going to find out the f of n, which is the exact amount of time that it will take for a problem of size n to solve? Or do we really just kind of need to know how it compares to another algorithm? Just need to know how they compare. Okay, you know, all the constants, you know, all the coefficients are not as important. So that is why we need to, you know, study the time complexity of algorithms, which is translated, you know, very loosely. That's basically asking, how does the amount of time scale with the size of a problem? That is called the time complexity of an algorithm. Do we have any questions at this point about the concepts of what is the time complexity of an algorithm? Okay. Yep. Mhm.
When will we know if it has to be like log?
Well, there's another module that talks about, you know, how we can do this, how we can determine the actual time complexity. So right now, we just have to kind of understand the significance of time complexity. So your question will be answered in probably another week. But, you know, right now, we just want to understand why this is important to us. So just to give you another example, okay, how many of you still remember the binary search algorithm? Assuming an array is already sorted, I want to find a particular item, and you remember what binary search is about. No, that's a linear search. So binary search, you divide, exactly. So how do you divide? By divided by half, right? So binary search is basically looking at an entire array. And it has to be sorted, okay? In order for binary search to be applicable, the array has to be sorted. So what you do is you take the entire array, you pick the middle element of the entire array, and you compare what you're looking for with that item. You have three possible outcomes, right? One is what you're looking for is larger than, it can be equal to, it can be less than. If it's equal to, okay, good job, okay, you just found it. But more likely than not, it is one or the other, which means it's larger than or less than. So if it is larger than, you can remove one half of the array because that particular half of the array would be less than what you're looking for. And as a result, we can just get rid of that. And vice versa for the other result of comparison. So that means, you know, with every single comparison, you remove about one half of what is left that can potentially contain the element that you're looking for. Okay, it doesn't sound like much, does it? So let me give you this question. Let's assume that the world population right now is 8 billion, we have just exceeded 8 billion, but let's just assume that it is 8 billion. And we have a global directory, based on some kind of ID. So how many comparisons is it going to take me to find 8 individuals within 8 billions of records based on a particular ID? Oh, it's not. It is not. Remember, we are having with every single comparison. So that means after the first comparison, we only got 4 billions left. After the second comparison, we only got 2 billions left. After the third comparison, we only got 1 billion left. So it doesn't sound like much because after 3 comparisons, we are still looking at 1 billion. But when you look at the rate of decrease in terms of how many more or what is the size of the remaining array that we need to look, it is always 1/2 or a little less than a half from what it used to be. So the question really boils down to, if you were to divide 8 billion by 2, how many times can you do this before it becomes 1? And that becomes a log question. So if you take the log 2 of 8 billion, that will give you the answer directly. If you have a calculator that can only give you the natural log, no problem. Take the natural log of 8 billion and then divide it by the natural log of 2. That would give you exactly the same result. I don't even have to do that. It's 33. How do we know? Okay, so this is another trait, okay? 1,000 is approximately, it's close to 1,024. It's not exactly, but it's close, okay? So why are those two numbers important? Because 1,000 is what we like to use in base 10. Because 1,000 squared is 1 billion. 1,000 cubed is 1 billion. Okay, so we are used to thousands, okay? 1,024 is useful because it is exactly 2 to the power of 10. So now in your mind, you can say, okay, so 10 to the power 3 is approximately 2 to the power of 10. Is that okay? We good so far? What is a billion in terms of a power of 10? 1 billion is 10 to the power of 9. Very good. So how many 1,000 do we multiply in order to get 10 to the power of 10? 10 to the power of 9. 1,000 cubed, right? Okay. And if I just say, okay, for all practical purposes, 1,000 is 1,024, which is 2 to the power of 10. So what is 2 to the power of 10 itself to the power of 3?
Pretty close.
It'll be 2 to the power of 30, right? So 2 to the power of 30 is about 1 billion in base 10. And then we have the 8 to take care of because we are talking about 8 billion, but 8 itself is just 2 to the power of 3. So now you have 2 to the power of 3 times 2 to the power of 30, which combined is 2 to the power of 33. Okay, so if we double 33 times, we get 8 billion, which also means the other way around is true as well. If you divide 8 billion 33 times by 2, you get down to 1.
So this one scales pretty well.
Oh, it's super good because you do 33 comparisons. You can find out whether an ID is in the array or not. So even if it's not in the array, in 33 comparisons, you can find. Still discover.
At worst, like 4 billion.
Hmm?
Instead of like worst, like 4 billion, it's like all the way to the back.
Yep. And if the world population doubles again, you're just adding one more comparison. Yep. It's just 2 to the power of 34, and then we will have 16 billion people in that case. So I think that is impressive. Okay, with 33 comparisons, you can find a single thing in an array that has 8 billion items. So that really is a dramatic way to show you, why time complexity is important. Because if you were to use linear search, okay, then it's going to be proportional to the size of the array. So on the average, assuming what you're looking for is randomly distributed, then on the average, you will still need 4 billion, comparison as opposed to 33.
It's a little bit.
Yes, and most people cannot really comprehend, scale once it gets past 100. Because, we cannot visualize, okay, not easily, and we cannot touch, feel, the scale that is more than 100, times. So, when it gets down to billion, it's not something that can easily be perceived by a person. All right. So I'm hoping by now you are getting, you're understanding why this is an important subject. So we are gonna go to some terms here. Okay, so I know these terms are going to be a little bit difficult to understand, but it does relate directly to relations. Okay, so this is kind of how we connect the topics. So we'll say that A is a partially ordered set. Okay, so I'm hoping you guys can remember what is partially ordered. If you don't, it's okay because it is restated here. In order for a relation to be called partially ordered, it has to be reflexive, which means an element has to relate to itself. Okay, it has to be anti-symmetric. Okay, which means A R B and B R A implies A and B are the same. Okay, and then we have being transitive. Okay, which means A R B and B R C implies A R C. Okay, you guys still vaguely remembering that? Okay, I'm hoping that the exam too will help jar your memory. Hopefully not in a traumatic way. So in this case, the less than or equal to relation, fits that bill. Okay, less than or equal to fits the bill. Okay, so let's double check and make sure that it makes sense to us. Is less than or equal to reflexive? Is a value less than or equal to itself? Okay, the or equal part takes care of that, right? Next, if A is less than or equal to B and B is less than or equal to A, does that imply A and B are the same? Yeah, makes sense. And is it transitive? In other words, if A is less than or equal to B and B is less than or equal to C, does that imply A is less than or equal to C? All right, so intuitively, it makes sense to us. Very good. So now we choose a subset X that belongs to A. So A is representing the set where the less than or equal to is defined over. X is a subset of A. So that means A has some of the values of X has some values of A. We'll define the predicate P of YX to be this universally quantified statement. So we'll just kind of pause here and double check and make sure that we understand what P is representing. So P of YX means for all lowercase x in X, for all element X in the set X, X is less than or equal to Y. Okay, what does that mean? Well, that means, Y is, it means Y is the maximum of every element in X. Not quite, okay? Very close, but not exactly. Why not? Because there's no requirement that Y has to be in X itself. Okay, so that one little thing means, this is not quite exactly the same thing as finding the maximum of, in the set X, but it's close, okay? So Y can be outside of X, Y does not have to be an element of X itself. So we'll just call Y an upper bound of X. Nothing in X is greater than Y. Yeah.
So what? So it doesn't have to be in X. So what does Y on the X mean then?
You mean this part here? These are parameters. These are parameters to the predicate of P.
Oh, so just the input.
Yeah, these are just parameters, and so that we can refer to Y over here, and we can refer to X over here. So they're just parameters. This is how we define the predicate P. Okay, so as I said here, the predicate P YX means that Y lowercase is an upper bound of uppercase X. So now we're going to define something else, which is the supremum definition. So S is the supremum of X, because only if P of Sx is true, which means S is an upper bound of X, and for all S prime, P of S prime X implies S is less than or equal to S prime. Okay, so let's take a moment here and try to digest what that means, okay? Because I know I could have taught this class using just plain English, just as I could have written my dissertation in plain English. But it is important for you guys to learn how to read these statements, because when you move on to a 4-year university, there will be a class called the analysis of algorithms. And that's all they do in a 3-unit class as an upper division class at a 4-year university. They will just all you're going to do in that class is not to write any code, any program. And instead, you'll be studying algorithms and try to figure out the time complexity of those algorithms. And these symbols will come in handy. So we'll break this down and try to find out what it means. Okay, so we'll start with P of Sx as a predicate. Okay, we know what that means. It just means that S is a upper bound of X. Now note how I use the word a instead of the. Okay, which means it is one out of potentially many. That is important, okay? So the upper bound, there can be multiple upper bounds with respect to a certain set. Does that make sense? Okay, all right. So what about the second part after the conjunction? So this one, is a little bit more complex. It says for all S prime, okay? So S prime itself is universally quantified. And it says right here, P of S prime X implies blah, 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 which means that if S prime is a upper bound of X, then S should be less than or equal to S prime. So together, what does that mean? S itself is an upper bound. Yes, go ahead.
S is an upper bound.
S is an upper bound, so is S prime. So is S prime. By the time we get to the implication,
And S prime is bigger than.
it says the S has to be less than X prime. Yes, that is correct. So we are looking at the smallest upper bound with respect to X. That's all it's saying. Are we good? Okay, so far, we're looking at the smallest upper bound with respect to X.
What do you mean by S prime? Is that like? Just like a.
S prime comes into existence because of the universal quantifier. So that means, if S prime is not a upper bound of X, it's okay. The implication is automatically true, in which case we don't care how it compares to S itself. So the only time we have to look at whether S is less than or equal to S prime is when S prime is also an upper bound of X. So S prime can be anything, but if it is not an upper bound of X, I don't really care.
Yep, you have to use S prime as a variable.
You can use other terms. If you want to use T, that's fine. Yeah, I just use S prime because it is also a upper bound. Okay, so if I were to say this in plain English, I would try my best. If it's basically saying, S itself has to be an upper bound, but all the upper bounds have to be greater than or equal to this particular upper bound, which makes S the smallest upper bound with respect to the set X. Is that okay? All right. Yep.
Give us an example like
Sure, I can give you plenty of examples here. This is actually one of those easier items where we can generate examples. So do not be shy to ask for examples. Most of the time I can do it, very occasionally there are concepts that are much harder to make examples of, but in this case it's not. No. All right, so we are going to look at the original set first, okay? So we're gonna say A is the set of natural numbers, okay? First, so, and then I choose X to be a subset of natural numbers. And it doesn't even have to be a contiguous block. I just have to pick certain elements from the natural number. So I just choose 0, 5, and 9, and 6, and 11, and then 7. Okay. Is that okay? Is this still valid? Is X a subset of the set of all natural numbers? Okay. So now I'm asking, what qualifies as an upper bound with respect to X? Anything that is greater than or equal to 11 in this case, okay? So that means S can be P of 11X is true, right? Because 11 is an upper bound, it's the tightest upper bound. But then, P of 1100X is also true. Does that make sense? 1100 is greater than or equal to every single element in X. Does that make sense? Yep.
So now the supremum is
Mhm.
11.
The supremum is 11 itself because it is the smallest of all the upper bounds.
And the upper bounds are always given explicitly.
It is parameterized. So we are trying to find, you are given X, okay? You are given this thing here, you're given X, and the supremum is basically the smallest upper bound with respect to these values. And you guys, yeah, go ahead.
Oh, it's not the max. Not the max value.
In this case, yes, that's a very good observation. It is also basically just known as the maximum from our perspective because of one special property of natural numbers with respect to the relation less than or equal to. You guys still remember what makes a relation not only partially ordered, but totally ordered? Comparable, right? So now the question is less than or equal to comparable over the set of natural numbers? If I pick any natural number, can I say one is less than or equal to the other one? Yes, okay. Okay, so you turn your head, so you must be thinking about a counter example.
Yeah, I'm just trying to understand what comparable means in the sense of like less than or equal to.
So comparable in this case means, for all, okay, I'm using a plain text editor, so I can't use the symbol. So basically it means for all X, Y in the set of natural numbers, X is less than or equal to Y, or Y is that less than or equal to X. And the answer is yes, okay, with respect, if we're dealing with a natural number set, and we're dealing with the less than or equal to relation, then you pick any natural number, give me two natural numbers, they can be even the same. I can say, it's one or other. Okay, it's not exclusive or because X and Y can be the same, in which case they are both true.
I was just confused why you said A be a partial order instead of just saying it's a total order.
Because this concept also works when you have a set, when you have a relation defined over a certain set that is only partially ordered. So most of the time, if you're working with actual values, then it's going to be totally ordered. But there are cases where you might be working with tuples that are only partially ordered. So you may have, like a player stats in the game, right? And you prioritize certain things. It's like, if you spend more money in this game, then I don't even need to look at your win-lose ratio. You are a better player than the other player. So you can define those things where it is only a partial order. So the definition of supremum works on partially ordered relations as well. So that makes it kind of unique because now you don't need something that has to be totally ordered. You can work with something that is only partially ordered. Yes?
So can you give us an example where the supremum is not the max?
Is not the max. That is a good question. No, he's asking about the supremum, not the upper bound. So, if I'm using natural number, then it has to be the same. In other words, if we are dealing with actual real numbers, natural numbers, and so on, then the supremum is really a fancy name of the maximum. Okay. Is that okay? So Marcus, you made a very good observation. That is actually true, that the supremum turns out to be just the maximum when we have a relation that is totally ordered, which in this case, less than or equal to is totally ordered with respect to natural numbers or real numbers. So very good. All right. But it will also work in a set that is not totally ordered. It only requires it to be partially ordered. So note that the supremum of x may be different from the maximum of x. This is because the supremum needs not be its element of x, but the maximum needs to be an element of x. So that's one of the differences. Okay, so once we define maximum, we can define minimum. So infimum is basically the same thing as the minimum. Okay, so it's the fancy name. It is defined using some, equivalently, obscure notation, but it's basically the same thing that we had earlier. So now we have defined maximum and minimum. And then the third thing we're going to define is the limit of a sequence. This is where, your pre-calc prerequisite is going to come in handy. How many people still remember the most fundamental concept of calculus, which is taking the limit, right? So this is also related to limits. So we'll take a look at what it means. Okay. So now we are working, unlike calculus, which is a continuous thing, we are given a sequence of numbers. Okay, which means you're basically given an array of values. And the array has an infinite number of entries. So this is the sequence. It is a tuple starting with x0 and then x1 and so on. So the question is, what is this particular expression? How does it evaluate? Or what it means when I say it equals to k. Right? So we'll look at this again. Okay, we'll take a second look at this one. It says the limit as I approaches infinity, x of I equals to k. What does that mean? The limit is k, and what does that mean when we say the limit is k for a sequence of values? Yes.
If I remember that. It's approaches because it keeps increasing until it approaches, but doesn't necessarily equal.
It says it's okay. So the more intuitive way to say this is the sequence will get closer and closer to k. Okay, but that's an awfully vague method of saying that. Okay, so let me say that one more time. If I say, when you take the limit of the sequence, when I approaches infinity, x of I, which is referring to a particular element in the sequence, equals to k, it basically means we are getting closer and closer to the value of k. Okay, but that is really awfully vague. So instead, we use this notation here to express the same thing. It is obscure. It is not natural to us because math is a language. This class is like a language class because we are basically switching from natural language to a very specific way of expressing these concepts. So when we look at something like this, what do? The first instinct to many people is to go, I don't know what it is. I'm just going to give up right here. Okay. But you got to dig this through. Okay. This class is a lower division class in a 4-year university. So you can do this. Okay. You can do this so you can move on to the 4-year university and then you can move forward from that as well. All we need to do is to do this in a structured way. Okay. So we look at this and then we just do it step by step. The first part says for all epsilon greater than 0 and the epsilon being a real number, the following has to be true. So all that is trying to say is to say, hey, give me an epsilon, and the only requirement for this epsilon is it has to be greater than 0 and it has to be a real number. Okay, so that means by the time we get to the inner part of the parentheses, we are basically saying, okay, I am now given an epsilon. And the only requirement of this epsilon is it has to be greater than 0 and it has to be a real number. So what do we do with this epsilon? Okay, and it says there exists an m in the natural number such that blah, blah, blah. Okay, so let's pause right here. Okay, so at this point, okay, by the time we get to the second nested level, we now have an epsilon, and then we have a choice of m. Okay, the epsilon is given to you, but you're kind of free to choose an m to make whatever is in the parentheses, in the innermost part of the parentheses, true. Are we doing okay so far with, are we doing okay with that concept? Let me point to the values here. If somebody says, hey, Tech, this is the epsilon, I'm challenging you, this is the epsilon I'm giving. The question is, can I find an m as a natural number such that this part is true? So I do have a choice of which m I want to use, but whatever I choose has to make this part of the expression true. Okay? So what does that innermost part of the expression say? It says for all j that are greater than or equal to m, and j has to be a natural number as well, the absolute value of k minus x of j has to be less than epsilon. What does that mean? What does that mean? So I think for this part, I am going to use, what is that? Zerno++. Okay, so give me a second here to set up Zerno++. But meanwhile, you guys can kind of try your best to understand the concept. Now, this is one part of math where it is truly abstract. And I can use graph to try to help illustrate the concept. But in the end, it takes a little bit of pondering to really absorb what it means. Okay, but I will try my best to kind of illustrate it using a graph. So give me a second here to prepare all that stuff. Here. So there we go. And then one more thing I need to do is fix the stylus orientation and resolution. So I'm all good to go here. All right. So what this means is we can look at a normal, graph like this. This is x, this is y, right? And k is here. Okay, so k is specifically this value. So when we look at the sequence of x, okay, so this would represent, x0, this would represent x1, this would represent x2, x3, and so on. So they don't have to be in a monotonic way, but basically they have to keep, it has to get closer and closer to k, like so. So that means, so what is epsilon in this case? Okay, let me give you another graph here. So if we go to the next page, like so. This is k, and we'll say, this is epsilon. Okay, from here to here is epsilon, and it is the same thing from here to here as well. That is also our epsilon. Is that okay? So epsilon is defining, plus epsilon and minus epsilon. And so when you extend out, these two lines, okay, it's defining a band of values for the sequence. Okay, then you go like, okay, so now we can kind of visualize how epsilon is used. It is defining a band that is centered at K. What about M? Okay, what is the special meaning of M? So we'll just kind of randomly pick an M here. So this is these are the i's, okay, x of I. So we're going to say M is here. Okay, this is 0, this is 1, this is 2, this is 3, all the way, and this is F. Are we doing okay so far? So the x-axis is really just all the natural numbers. So I'm saying that if you give me this epsilon, I'll be able to find M over here. And the guarantee is everything after M will be within the band. That's basically what a limit is trying to say. Is that okay? Let me say that one more time, okay? Because it does take a little bit of time to absorb this. This is a little bit abstract. K is the limit of the entire sequence that is given to us. The question is, what does it mean when the limit is K? It means that someone can challenge me and say, hey, Tech, I'm giving you this epsilon of 0.05, okay? Okay, so I am 0.05 over, 0.05 under. So now I'm defining a band. And then we look at this band here, and I just have to go find a place within the sequence where every value after this and after this particular index, they all fall within the band of K plus or minus epsilon. Is that okay? So you go like, oh, okay, so that works for when epsilon is 0.05. I'm gonna make this challenge a little bit harder. What if epsilon is 0.0005? Okay, so in other words, we're now looking at a much smaller band like this, right? And you go like, oh, this M is not going to work with that. Okay, but guess what? If the limit is holding, if that limit statement is true, that means I just have to go a little bit further out, starting from here. Okay, all the values in the sequence will fall within that band. So as long as I can find an M, okay, given any epsilon you can give me, then the limit statement is true. So let me switch back to the discussion here. So this statement is simply saying that no matter how small you make that epsilon, I will always be able to find that index M so that all the values at index M and past that will fall within the band of K plus or minus epsilon. Is that okay? Okay, do you remember that this resembles a little bit of how derivative is defined? Except in that case, they have a delta, right? So that's how a limit is defined. So that this means K is a unique value that satisfies the requirement, blah, 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 which we just talked about. But are you guys feeling a little bit more comfortable now reading the notation? Okay, all right. And this one is kind of nasty because it is a triple nested, kind of statement where we have a for all on the outermost, and there exists in between, and then another for all in the innermost part. So you basically have to look at each one separately, and then just kind of continue to parse the statement and to find out what it means. Are we good so far? All right. So not all sequences has a limit. And one really simple sequence, which is defined here, x of I is simply -1 to the power of I. This thing has no limit because it keeps oscillating between 1 and -1. So it cannot have a limit. I just realized that I forgot to do one thing that I said I would do earlier. So let's go back to do that one. I'm so sorry that I forgot to get back to that one, which is to use proofs by induction to give you guys examples of proof by induction. So I'm going to go back and talk about that one. And I promise you, this one is not going to be difficult. You guys can help me do this too. So you guys can focus on the right-hand side and I'll focus on the left-hand side. Yes.
Talking about the go over when you mentioned construction. have different limits. For
Not in this case, because we're going to find out that limits has its problems. So we're going to use another approach to define the upper bound and the lower bound. Yes. All right.
Will those be different, but they're the same.
We are probably not going to even matter, it's not going to matter to us, so I don't think we're going to make a distinction in this fact. All right, so we're going to prove this particular theorem. We'll just do the first one first. So I am giving you a definition of f of n. F of n is defined to be, if n equals to 0, then f of n is 1. If not, f of n is defined to be twice of f of n minus 1. That's the definition. It's a recursive definition, but nonetheless, I'm defining a function for you. Is that okay? The theorem is basically to say that as long as n is a natural number, f of n is 2 to the power of n. That's the theorem. How do we prove it? Is that okay? So the way we prove it is first we ask the question, what is the basis? In other words, can you find a value for n where I can just kind of plug it in and I get the equivalence right away? So since we are dealing with a natural number, so the natural choice is going to be 0, because 0 is one end of all the natural numbers. So now we basically say when n equals to 0, then what do we get? Then f of n is 1 by definition, and then 2 to the power of n is also 1 because of the power function. Does that make sense? So that means f of n does equal to 2 to the power n when n equals to 1. So I'll just make it very clear here. Therefore, f of n equals to 2 to the power of n when n equals to 0. Have you get so far? And I know we have limited amount of time, maybe 2 minutes, but that's all we need because this one is super easy. So in the induction step, we have an induction assumption. The induction assumption is basically saying for some k, we say that f of k is 2 to the power of k. That's the induction assumption. We're basically saying, yeah, we know up to this point, the theorem is still open, okay, up to the value k. So the actual proof is to basically say to ask, what about f of k plus 1? Okay, so f of k plus 1, by definition, equals to 2 times f of k. Are we doing okay with this part? Okay, so we can basically say, okay, it's no fun when k equals to 0, right? Because it's just the basis. So you say k plus 1 is going to be non-zero, and as a result, it is 2 times f of k. But based on the induction assumption, f of k is 2 to the power of k. So now we have 2 times 2 to the power of k, and that becomes 2 to the power of k plus 1, and therefore we have the induction step proof. Is that okay? Does that make sense to you? Can everybody kind of connect all of these steps? Okay, f of k plus 1 equals to 2 of f of k. That's because of the definition of k itself. 2 of f of k equals to 2 of 2 to the power of k has to do with the induction assumption. All right. And then the last part of combining the 2 times and the 2 to the power of k to turn it into 2 to the power of k plus 1 is just algebra. And that's it. Proof by induction is done when you have the induction step itself proven. So now the theorem is proven, and we still got some seconds left. So the approach is deceptively simple. And it is also very powerful because every single time you have anything that is expressed recursively, it lends itself to this type of technique to prove the algorithm is correct. Okay, all right, so you got your work to do. I will post the questions as an announcement. So this way you all have access to it. And then we'll talk about it next Monday. Have a nice weekend. Well, it looks like it's gonna be nice weather.
My mom,